due to lack of time, but if you want to talk to me about that offline, I'll be happy to show you what we did there. Now, why do people look at storm surge models? Well, there's really two reasons, and for many years we were looking at storm surge models for the purpose of hindcasting. So going back and studying historical hurricanes, and actually the first hurricane that we ever looked at was Betsy, which hit New Orleans in 1965, and was really the last major storm that affected New Orleans before Katrina. And the reason that we look at hindcasts is to evaluate inundation risk in coastal areas. So as we heard, high impact, low probability events in an evolving system. And it's critical to designing protection and mitigation systems in order to reduce that risk. Now, as we have increased our computational power, we can use the same tools that we use for hindcasting to now do forecasting. As storms approach land, of course, you want to make an estimate of what the maximum surge is going to be and give that estimate to the emergency managers. We work with the Texas Division of Emergency Management, so anytime a storm is approaching Texas, we run our model, we give them the results, and they use that to, along with other model results, to make decisions about evacuations and where to deploy first responders. But forecasting, of course, is very different from hindcasting. Hindcast can be done very carefully with very high-resolution simulations. Forecasts have to be done more or less in real time. So 2 hours is sort of the time limit of a forecast. However, with the computational resources that we have now, we can often use the same grids and everything that we use for the hindcast to do the forecasts. So what are the physical processes in storm surge? Well, of course, the predominant process is wind. And for us, that's a one-way coupling. We get wind data from other sources. In forecast mode, we use a dynamic Holland wind model. In hindcast mode, we usually obtain winds from a number of sources. NOAA, there's some private companies that generate winds after the fact. These are data assimilated winds. So that feeds into our model as a wind stress. And we also include wave-current interactions, and that's a two-way coupling. So we have a separate wave code which calculates wave radiation stresses, feeds that to our code, the circulation model, and then we feed the currents back into that wave code, and I'll talk a little bit about that. Tides are an important effect, atmospheric pressure, and riverine flows, especially in areas like the Louisiana area where you have the Mississippi River coming down and interacting with the surge. Wetting and drying, of course, is an important effect in coastal inundation, which we have to model, and that's sort of done in a dirty fashion, sort of an engineering approach. Now, the last two things that I mentioned here are things that we don't have in our model. Rainfall, which is important, but it's a small-scale, very local event. Most rainfall models that are out there are sort of discrete network models. Of course, they have to run very fast, but we're doing research now on how to couple those models with our more physics-based models. And sediment transport and bed morphology. We've made some efforts in this area in the past few years, but coupling that with our surge model to do scouring in real time as a hurricane is hitting land is also a very challenging problem. So an overview of our modeling system, we prefer to use large domains to model the basin shelf coastal interactions. This requires extensive data collection for bathymetry, topography, land cover, etc. I'll show you some of the domains and what kind of data we have to have. The models that we use are ADCIRC, which was mentioned in Carrie and Manuel's talk. That stands for Advanced Circulation Model. That's our shallow water model. For waves, we use SWAN, which was not our code. It was actually developed at TU Delft. And then we have various wind inputs, as I mentioned, from NOAA, and then a couple of consulting companies, Whirlwinds and Ocean Weather Incorporated. So ADCIRC uses a finite element discretization. We have the traditional model is a continuous Galerkin model, which is all I'll talk about today, but we also have research in looking at other algorithms such as discontinuous Galerkin methods, and this is ongoing. And the codes, both ADCIRC and SWAN, are parallelized so that we can run them on these large multi-core machines that are now available to us. Some of the applications of the model, it's been used for all the levee designs, the new levees that are going up in southern Louisiana. We've used it for the digital flood insurance rate maps that FEMA has to develop for determining eligibility for federal flood insurance. We have primarily been interested in the Texas region. And actually, the FEMA project has paid for a lot of the data collection, so it's been very beneficial to us because we have to have pretty high-resolution data for those kinds of runs. And here we're using, synthetic hurricanes, much in the flavor of what Carrie Emanuel talked about this morning. We're running about 450 storms to see the impact on the coast. In forecasting mode, we use ADCIRC for primarily Gulf storms, but my team uses it for Texas storms. LSU uses it for Louisiana storms, and then our collaborators at North Carolina use it for East Coast storms. And then it's used by the Army Corps of Engineers and the Navy worldwide. Now, this slide got messed up in the transition, but SWAN, I just wanted to show some math here. So SWAN solves the action balance equation for this quantity N. It's actually a 5-dimensional equation because we have geographic space and spectral space and time. These velocities, CG, C theta, C sigma, are called Greek velocities. They're dependent on a number of things, but they're also dependent on the current, U, and there's a lot of physics in that source term, S, on the right-hand side, which accounts for wave interactions and refraction and so forth. And I just show here the algorithm, but I won't go over that. So that gets coupled to our circulation model, ADCIRC, and ADCIRC actually does not solve the traditional shallow water equations. It solves another variant of the shallow water equations called the generalized wave continuity equation, which is obtained by manipulating the shallow water equations in a certain way. And so we solve for the water elevations data using this second-order wave equation at the top, and then we couple that with the vertically integrated momentum equations. And if you look at the right-hand side of the momentum equations, you see a lot of these. There's a lot of source terms. So there's, of course, bottom stress, bottom friction, all the source terms that have to do with the wind and the wave radiation stresses. There's eddy viscosity, there's atmospheric pressure, tidal potentials, and so forth. So a lot of the physics is driven by the source terms on the right-hand side. Now I mentioned that we use very large domains, and for us that would be a typical domain would be the western North Atlantic Ocean. So this is a graphic of the bathymetry of the western North Atlantic. You can see the outline of the East Coast, Florida, Gulf of Mexico. So the colors represent bathymetry. So blue is deeper water, then you see the continental shelf, and then you see the inland areas. And we use an unstructured triangular mesh, so this gets discretized into very meshes, triangles of different sizes. Of course, if we're out in the deep water, those triangles may be on the order of kilometers. As we transition through the continental shelf, maybe on the order of a kilometer. As we get down into the coastal inland regions, we're down into the 100 meters down to 50-meter scale. We zoom in, for example, in southern Louisiana. This is the topography and water depths in this region. You can see the Mississippi River over there, Lake Pontchartrain, the New Orleans area. We include in our domain up to about the 18 meters above sea level, just because that is the area that could potentially be inundated by a very severe storm. This is a zoom on the New Orleans area. And you can see all these sort of brown lines. These are levee systems. Of course, the Mississippi River has a levee on both sides all the way down to the Gulf of Mexico here. And you can see the very fine networks of channels, other levee systems, the levee system in the city of New Orleans, the barrier islands, and so forth. And so to a large degree, these get incorporated into our mesh. We try especially to incorporate all the levee systems, barrier islands, many of the fine-scale channels, because anything that could be a conduit to surge, we need to try to incorporate into our domains. And this is moving over to Texas, so similar type of domain. We go all the way up to the 18 meter above sea level. That includes the city of Houston. This is Galveston Bay. You can see that fine line through there is the Houston Ship Channel, which goes all the way up into the city of Houston, which is a natural conduit for storm surge. There's a tremendous amount of economic infrastructure in this region. This is where all your oil is refined, your chemicals are made, and this is a huge economically important region. And this just shows the discretization of that region. So again, a lot of the fine scale features get included in the model. Now focusing on the 2005 hurricane season, I'm just going to talk about Katrina. So we all know a lot about Katrina. It was a very strong storm, tremendously wide storm, had a huge surge behind it. Did a lot of damage in the city of New Orleans. This is Rita. I won't talk about that. And this is a movie, a simulation using ADCIRC and SWAN of the event. So you can see the arrows are the wind speeds and the colors are the water levels. And the scale there is on the order of meters. So you can see initially when the eye first passed over the Mississippi River Delta, there was a tremendous amount of surge that piled up against that levee system in Mississippi. In Louisiana, in what's called Plaquemine Parish, down in the Delta region. That did a lot of damage. And then, of course, the hurricane proceeded and then made landfall in Mississippi, where they had about 8 to 9 meters or 10 meters even of surge. It was a tremendously, the largest surge, one of the largest surges ever recorded. And of course, the storm pushed a lot of water from east to west into Lake Pontchartrain. And when the wind turned from to north to south, and that pushed water into the city of New Orleans, and that did a lot of damage in terms of the levee failures.
Can you say how much time
This is probably about a day, well, between 12 and 18 hours. I can't remember the exact, but so it made landfall early in the morning first in Louisiana, then it made landfall again later in the day in Mississippi. This is what the maximum water level, so this is taking the maximum at every point in the domain and just plotting that. So you can see the tremendous storm surge in Mississippi and also the surge that built up along the levee system. You can see the surge that stressed the New Orleans levee system. Now we don't account for levee failure in our models, so we don't actually model the flood of New Orleans. Now this is comparisons between the model and data, and the green here represents errors that are between half a meter plus or minus half a meter. You can see that throughout much of this region we have a good agreement between measurements and our model. Now there's some regions, blue regions, where we're off by as much as a meter, even more, and so those areas require further investigation. And this is just a scatter plot showing for all the measurement locations comparisons between model error and data. This is the results of SWAN. This is the significant wave heights, and you can see the tremendous waves, but those waves broke along the continental shelf. So the wave model tends to help push water up onto the continental shelf, and then that increases the surge inland. But you don't see huge waves coming inland, at least not with the SWAN model. You'd really need a nearshore, a more accurate nearshore model to get that run up onto the coast. Some of the lessons of Katrina, of course, there was this IPET report that cataloged all the failures. It was a strong Category 3 storm, but had a devastating storm surge, so wind intensity and storm surge are not directly related in many cases. There's been some lawsuits as a result of Katrina, of course, due to the levee and the flood wall failures, and the ADCIRC model has been instrumental in some of these lawsuits. The levees are now being built back to withstand a Cat 3, so the question is this good enough? And a long-term question really is what to do about these Mississippi River levees. They are detrimental in many respects. They do protect the coastal communities, that have grown up around them, but they tend to cause sediment to just be dumped out into the Gulf instead of replenishing the delta. And they are protection against storm surge, but at what cost? So moving to 2008, there were two major storms in 2008, Gustav and Ike. I'll focus mainly on Ike. I just want to mention one thing about Gustav. So Gustav tracked to the west of New Orleans. There was a significant amount of surge that came from east to west. It was, again, a pretty big storm. Came to the east side of the New Orleans area. And one thing, this marsh here, this huge marsh, should have been a pretty good barrier to the surge. But in fact, that marsh was completely inundated, and the levee at the end of that marsh was almost overtopped. And this violated the sort of back-of-the-envelope calculation that people typically make about wetlands being good surge protectors. And so this is really an ongoing area of research, is how beneficial are wetlands to attenuating storm surge? There's really some interesting questions there. Of course, it depends on the type of wetland. There's a lot of questions there. It almost overtopped some of the levees in New Orleans, some of the flood walls, but those have been built back. This just shows the track of Gustav. And at this particular time, these are the winds. So you can see it was a big hurricane, lots of very wide wind field. These are the significant wave heights. Again, they break as we come up onto the continental shelf. And these are the water levels at this particular time. So again, there was quite a bit of surge, not nearly as high as Katrina, only about 3 meters along this levee system, and then this little V thing that's called the catcher's mitt in east of New Orleans. There's always a lot of surge there, and into Lake Pontchartrain. So Gustav stressed the New Orleans protection system, but it didn't break it. The wetlands and marshes east of the Mississippi River did not attenuate surge as expected. However, the wetlands west of the Mississippi River did help attenuate surge. So there was some discrepancy there. And again, this was a strong Category 2 wind. Most of the damage from this storm was from wind. Now moving to Ike. Ike happened about 2 weeks later. This was a potentially very, very devastating storm. It started out as a very strong Category 4. It made landfall first in Cuba, and it weakened. Came back out into the Gulf, and then strengthened, and then headed straight for the Houston-Galveston area. Now, Ike had a very interesting phenomena attached to it, which we call a surge forerunner. And this seems to be a particular characteristic of the Texas-Louisiana shelf. As you come off the Mississippi River Delta there and you go in southwestern Louisiana and then down the Texas coast, it's a very broad, sloping, slick continental shelf. It propagates waves very quickly. And so once the storm surge comes around that delta, you'll see it just sweep down that shelf very fast. And what happened was that because of that and because of other factors, there was about 6 to 8 feet of surge 24 hours before the storm even made landfall. This had been recorded back in the 1900 Galveston hurricane, and actually Ike and that very devastating storm, which killed about 6,000 people in Galveston, had very similar characteristics. Their track and intensity were very much the same. So as we, again, this is a simulation, and I'll go forward to, as you can see now, the surge is starting to come off the Mississippi River Delta and propagate to the west and then zoom. So 24 hours before landfall, we have between 2 and 3 meters of water building up along the Louisiana-Texas shelf. This is partly due to the Coriolis effect and also due to just the bottom friction characteristics of that shelf. Notice that the wind is blowing either shore parallel or offshore. As we proceed and the hurricane makes landfall, then of course at the last minute the wind field turns toward the coast and we get that huge push. And there was between 5 and 6 meters of surge to the east of the Houston area. And Houston really dodged a bullet on this storm. If the landfall had been 10 miles down the coast, it would have been much more devastating for Houston. And this shows the recession of the surge. So just comparing again measurements to data. These are hydrographs. Black is data, red is our model. As we move around the Gulf, we do a pretty good job of matching the surge, especially the maximum surge, at many locations. See, sometimes the measurements are kind of noisy. Sometimes you don't have a measurement for a while. As we move into Texas, you can see that lift in the data is that forerunner. We're getting some of it, but not all of it. So again, this is something that we're working on. So we get a pretty good match with the maximum surge, and at that location. There was a lot more instrumentation in Ike than there was in Katrina. There were a lot more measurements. I want to point this out. This is way up in the city of Houston, so they got about 12 to 15 feet of surge there, and the model actually captured that pretty well. And this is going down the coast. So even as far down as almost to Corpus Christi, there was a substantial amount of surge from the storm. Again, these are comparisons between high water marks or maximum elevations computed by our model and measured. And primarily green, meaning that we're within plus or minus half a meter. And I'll just show you that these are the significant wave heights during the storm. This storm produced tremendous waves. This is a swan simulation of that. And then as the storm moves up on the coast, those waves break. But pretty big waves, even up to the coast. And these are comparisons between swan and measurements of significant wave heights at various locations along the Gulf. So pretty good matches with data, many locations. Not so good as others, but validation, verification, and validation work is very important. So we are pretty diligent about trying to model as much data as it has to be good quality. So in terms of I took 4 runners about 60 water Texas has 24 hours landfall. This was also observed in the 1990 ADCIRC. Ike resulted in this coastal ocean along Galveston Island and involved in also these areas. Again, these are things that we would like to incorporate over our model in the future. And Ike was a strong category 2 storm that had a very large, wide storm. So again, category surge are not necessarily connected. I mentioned that we did forecasting. This was a forecast that we did by during the event. We didn't have good bottom friction characteristics, and we were using the Holland wind model. But we pretty much captured a major storm surge. So again, the major surge occurred east of Houston, and it was between 16 and 20 feet. So we got the major characteristics of the storm about right. I also want to mention that we run these codes in parallel, and this just shows the scaling on various machines that we run on. We do get good scaling. We have a new machine that's just come online at the University of Texas called Lone Star, which is even much faster than our Ranger supercomputer, where we've done a lot of our calculations. And so we continue to work to make our codes scalable so that we can make the best use of these machines that have been very beneficial to our research. I just want to close by saying that the response to the hurricanes has been interesting, going from state to state. So Mississippi, of course, they have a much smaller coastal population, And they had a concerted effort between the state and the federal government and even some nonprofit groups, and decided to move some of their vulnerable population and businesses to higher ground and return the coast to its more natural state. Now, Louisiana doesn't really have that luxury because, of course, a lot of it's under below sea level anyway, so the response there has been to build more levees, build up the Mississippi River Delta and wetlands, and try to save the barrier islands. Texas still hasn't really responded to Hurricane Ida. There hasn't been a coordinated response. And as I mentioned, if Ike had been 10 miles down the coast, so if it had hit at this P7 in this graphics versus the OL, which is the original landfall, there would have been a lot more surge in the Houston region. It would have been, and in along this eastern Gulf, western Gulf Galveston Bay corridor, where there's a lot of people, a lot of infrastructure, it would have been very devastating. There's some talk about building what's called the Ike Dike, which I think actually has pretty much been decided that that's not a good idea. But we ran a simulation with the dike in place and showed that it would help attenuate surge, but I mean, again, what would be the cost and what would be the environmental impact of such a thing? At a smaller scale, there's been some talk of just building a Rotterdam-style gate across the Houston Ship Channel, because much of the really heavy industry is in that little area going to the city of Houston, and that would be a much more cost-effective strategy and could, in fact, work in terms of protection. So let me just close by mentioning some research avenues. Of course, we're always looking at improved algorithms which capture the highly advective flows, the multi-scale flows that we're dealing with, and which are dynamically adaptive. All the grids that we use right now are static, and they're very expensive to generate and to use. We're actually doing a lot of overkill, I think, in terms of our resolution. We're looking at both conforming and non-conforming discretizations, HP adaptivity, local time stepping, and how to handle the tightly coupled physics. And as we add more physics, such as rainfall and sediment transport, how do we keep our algorithms stable? Modeling of wetlands is very important, vegetation, marshes, fluid structure interaction with bridges, seawalls, even down to the level of individual neighborhoods, streets, buildings. We're looking at using LES and RANS models in wetlands to try to upscale those to account for the frictional characteristics of the wetlands. Improved wave current coupling, including phase resolving wave models. What I talked about with SWAN is called a non-phase resolving wave model. And this is an effort that we have now in looking at a new model called the Green-Dagny equations. And then finally, I mentioned rainfall, sediment erosion and deposition. Of course, uncertainty quantification and data assimilation are things that we are just now starting to look at in terms of giving error bars on our calculations, including more statistics in our calculations, and actually trying to assimilate real-time data into our calculations. So thank you.
Thanks. We have 2 minutes for questions directly related to this talk. I'm going to ask the person asking questions to state your name and affiliation. Clint, you can repeat the question so we capture on the microphone and the webcast. Good. Questions for Clint? Stand up. Sure.
Okay. Tony Song from GTR. I have a question. How important the sea level, the sea surface temperature in your hurricane prediction in terms of the intensity and the landfall of your coral track prediction?
Okay. The question is how important is
Okay, the question is how important is sea surface temperature in our prediction? Well, we're not predicting track, so we're just predicting the storm surge. So we have to obtain the track information. All the wind and track information has to be provided to us. So we're not modeling sea surface temperature. We're not modeling the feedback into the atmospheric model.
I said the winds for us are just
So I said the winds for us are just the one data. So we obtain wind data, which becomes a wind stress for our storm surge model. And we don't feed that We don't feed anything back into the
We're not
atmosphere.
looking at the coupling.
So we're not looking at the coupling between
So
the...
you are not a hurricane model. You are the storm.
We're a storm surge.
Okay. Okay.
We're a storm surge model, not a hurricane model.
I'm Dave Jackson from UCLA, seismologist. Is there any reason why you and the first speaker, Professor Emanuel, couldn't couple the storm surge models with their synthetic hurricane models and provide some sort of longer-term prediction for what storm surges ought to be expected in a particular place and optimize and have a response?
So the question was,
The question was, would our group work with Kerry Emanuel's group to maybe look at what the storm surge would look like in the future, what we're doing in hurricanes. We're actually doing that. So Kerry mentioned in his talk that he is working with Hans Westering. So that's something that I think that collaboration will continue in the future. Kerry, do you want to say anything about it?
yes. Sounds like a great idea.
Sounds like a great idea.
Seth Stein from Northwestern. There was some sense after Ike that the National Weather Service had very much over-predicted the storm surge. And can you tell us about describe what happened or didn't happen? I mean, that's just from the meetings, but technically.
As I recall, the Swatch model predicted about 25 feet of surge for that storm, and it turned out to be about a 20-foot maximum of about 20 feet of surge. So this is typical with the Swatch model. It's sort of a better safe than sorry kind of model. It tends to overpredict surge in all the cases that I've seen. And it Swatches, they generate those surges by running thousands of synthetic storms that are similar to the event. They're not. I don't know that they're actually running the actual storm itself. They're doing many ensembles of storms. So it's sort of an ensemble calculation that they're doing here. It tends to overpredict. I've seen that in many situations.
I'm George from Nicolau, Stanford University. I missed the early part of your talk. My question is, what kind of equations are you using to do your numerical simulations? And by that I mean, you're using the shallow water equation, the diffusive shallow water equations. This is a very untidy field. There's a lot of competing things. And could you enlighten us as to how you decided what model to use and why? And what about the field itself, where there are competing claims and different strands of researchers doing different things in different directions in this area?
Okay, so the question was what models do we use?
Okay, so the question was what models do we use, and are there different models, there different opinions about what models should be used.
We use average shallow water equations.
Depth average shallow water equations, so the 2D shallow water equations for the simulations that I showed you.
Over an uneven topography.
There is?
Yes.
Over a variable topography.
Yes.
Over a variable topography.
Yes.
Over a what? Yes, with variable bathymetry.
This is sort of the standard model.
This is sort of the standard model in coastal engineering.
Different about our model.
I don't think there's anything different about our model than any other 2D depth average model would
There is some ongoing debate about whether
There is some ongoing debate about whether we should be running 3D models, 3D hydrostatic models, whether we're missing 3D effects. But of course 3D models are much more expensive to run. And so there's model-to-model comparisons going on now between various 2D models and 3D models as to how well they predict storm surge.
That wasn't quite my question. I really want to understand how the fronts, the surge as it's moving over the rough topography, it's interacting with a lot of scales. And there's are you modeling turbulence there? What are the issues there? The flow is not just a shock wave going over some flat surface like the shallow water equations would have over a flat bottom. There's a very complex interaction of the surge with the topography.
Right.
How is that treated?
Right.
Through bottom friction.
Through bottom friction. Through frictional parameterizations.
And that's an attempt to understand.
The subgrid scale effect of turbulence, yes.
So we use
So we use Manning's laws.
We use a
And we use a hybrid friction
law, which is a function of depth.
law, which is a function of
Also, the Manning's
also the Manning's which is a coefficient that depends on what type of surface you're flowing
over land.
So if we're flowing over land, that has to do with the land cover
So
characteristics.
that's what we use.
So that's what we're using as a Manning's type law.
Other questions?
The objection again. One thing that breaks my heart is reading about what's happened in Bangladesh, storm surges and huge numbers of people. Anybody trying to apply these kind of models to other places that don't have the resources that we have?
I'm sure there are.
I'm sure there are.
As far as
specifically Bangladesh, I don't know who is sort of responsible for doing emergency management in that area.
We don't.
We don't.
Our model
is not used for anything outside of the States, particularly on an operational basis. Our model is available. We provide it to download it. The difficulty, of course, is getting all the data that goes into the model. So you have to generate a grid. You have to have pretty good imagery and topography information. But
that information,
that information, even if you have a coarse grid, you can still get some. Still better than nothing.
I have a question. The Omar class in Texas. It shows comparisons in Ike in particular, a bunch of stations, and they look really good. Particularly that one station in Houston, which that station was on part of the original drawing, whether it's
At Houston Station.
So very complex geometry. You get all the uncertainties from those models, the physically, topography, the band and center. These are just this is just a pure prediction. There's no, you mentioned data simulation, future direction. It's not the only thing you get is these event velocities that we construct efficiently. And that fixes wind shear, and that's your true forcing. And the rest is put in a priori without something. So the question is, are we tuning the model?
Are we tuning all these data? So what I've showed you so far is not tuned all.
But I mentioned you and John.
I mentioned you and John
They do a lot of the
beginning. They do a lot of the data collection in terms of getting us accurate
questions about what's the right thing.
questions about what's the right manual
There's a lot of
to use and so forth. So there's a
trying
lot
to
of
make physics of the model as
trying to make physics of the model
accurate as possible before we go.
as accurate as possible before we go into the
Tune it to one location.
if we tune it to one location, it throws it off. So you really can't do that.
Presumably, in addition to state estimation, there's room for parameter estimation beyond
Right.
There's a lot of areas where we don't.
There's a lot of areas where we don't have good measurements. And that would be really interesting.
So Michael Stein, University of Chicago. So in actual forecasting mode, you have to forecast both the hurricane and the storm surge, right? So which is the weak link? The hurricane.
I mean, can I interject here? Because I think this is a short topic. If the community were given a data-driven computational resource for this problem, I think you'd find the decision would be to run a bigger ensemble of hurricane coupled with surge forecasts, because the uncertainty in the hurricane forecast probably swamps all the uncertainties we've been sort of tangentially talking about having to do with model parameters and things and others. Maybe there's a tendency for people on my side of business to think people on this side of business know what they're talking about before. But we think that there's so much uncertainty in the hurricane forecasts that from a practical standpoint, we should try to put resources into quantifying that uncertainty.
I guess the other thing is I'm interested is following up more on this ensemble approach. I mean, I know you said it was over-predicting. Is that because the elements in the ensemble over-predict, or that somehow the interpolation to the present storm causes?
I think it's...
So it's not the ensemble approach per se that's causing the over-prediction.
No, it's the way they handle their numerics.
Web question, I guess. Yes. Doesn't get adaptive spatial and temporal resolution lead problems in the subgrid scale parameterization scheme?
Well, I'm talking about sort of adapting the grid down to the scale that we currently use now, so down to the 10, 30 meter scale. If we're going to go down to very small scales, well, then yeah, we're probably using the wrong model. Then we need to probably be solving the Navier-Stokes equation.
Michael Gill, UCLA. Actually, two questions. One sort of fairly technical one, and the other one more of general interest. Let me start with the general interest one. We did mention that there is considerable argument about what to do with the levees on the lower Mississippi leads, and that you concluded saying building more of them. Isn't it loggerheads with actually reconstructing the wetlands and the natural landscape that would temper this? So this is number one, and number two has to do with uncertainty quantification data simulation. Taking, of course, Terry's comments into account, data simulation on these time scales really requires a very remarkable system of both observing and relating the information. So is that anywhere in place while you're just trying to simulate, to sort of do observing system simulation experiments in order to construct this?
Those are both good questions.
First question.
The first question about the levee system in Louisiana. I'm really commenting that was their response to the storms was to build more levees. I mean, that was the decision that was made. And
So I guess that levee system.
I haven't seen it, but I've seen pictures of it. It's going to be finished, or pretty much finished in 7 years. So that was remarkable response. Now, whether that's the right response.
So it's not the one you recommend, it's the one that is being pursued.
No, that's what's being pursued. That was the decision. The second question having to do with data simulation. Yes, you're absolutely right. We don't, at the moment, we don't have the capability to observe and relay information in real time. Now, there are a few stations that actually, for example, there's a Texas A&M Corpus Christi has what's called the TCOON network, which does relay. They have pretty much stationary buoys which can relay information in real time during an event. So what we have done so far is just exactly what you said. So if we had that information, could we use it? And this might also inform where to put it.
I'm actually trying to figure out where it would be best to put things if you had them. And,
that's something that we were doing research.
All right. Another question. Abraham Solomon from the Colum. You mentioned that in Gustav, the marshlands didn't do what they were supposed to do. Does that mean that you ran the simulation with the marshlands removed from your elevation model?
No, that's just what was observed. The question was, I said that the marshlands didn't do what they were supposed to do. This is just based purely on observations of what happened, what actually happened.
So you might overtop the level if the marshland wasn't there.
Excuse me?
But if there was no marshland, might have been more of it.
All I'm saying is there's a sort of generally accepted rule marshlands attenuate surge, so many miles of marshland attenuate surge by so many feet. And that rule did not hold during Gustav. That's all I'm meant to say. There's sort of a back of the envelope calculation, common, it didn't hold true.